Welcome to the College Knowledge Podcast, sponsored by the College Planning Network and Paradigm Financial Group. Whether you're searching for that right fit college, applying to college, or figuring out how you're going to afford it all, you're in the right place. You'll hear from deans, admissions counselors, student athletes, and scholars from esteemed universities and colleges around the country. We'll dig deep to uncover their insight and unique experiences. So whether you're a student gearing up for college or a parent with college-bound kids, sit back, relax, and listen. Like you, we have lots of questions. Our guests have the answers, and we're excited to share them with you. Let's get started. If you didn't know, we're on Instagram, Facebook, Twitter, and LinkedIn at Elite Collegiate Planning. Make sure to share and tag us. Hey, everybody. Welcome back to College Knowledge. I'm your host, Dave Kozak, alongside my co-host, Mr. Joe Kerins. Good morning, Joe.
Good morning, Dave.
And today we have this distinguished pleasure of interviewing Dr. Martin Elvis, astrophysicist at the Harvard Smithsonian Center for Astrophysics. Welcome to the show, Dr. Elvis.
Great to be here. Thank you for the invitation.
Yeah, I'm excited about this conversation. I think Joe's a little trepidatious on where we're going to go here because I can get off into the black hole, pun intended. So obviously this is college knowledge, and we're sort of trying to peel back the layers of the onion on higher ed. And my interest in this interview is understanding how you go from, obviously, you're college educated PhD, there's a direction and a pathway. And was it just a pursuit of passion, or you just found your niche? Did you choose it? Did someone get you there? Was it mentorship? Was it just from like the raw beginnings? And if you could just give us as a start a little bit of your history and progression into where you are.
Sure. Well, I had no understanding of higher education, like college, university stuff at all when I was in high school. I was in England, of course, back in the day. And as you can guess from my accent, so I was the first in my family to actually go to a university. So it was all feeling it out. I was pretty clueless, basically.
Okay.
And there was a sort of, in England, everybody wants to go to Oxford or Cambridge. And I was encouraged to apply. And but it turned out my school had no knowledge either about getting into those arcane places. And they said, "Oh, apply to this college. We have a special place for people from our high school." Turned out to be a divinity only college, and that was not really me. So they threw me out. So I just found places that were doing physics because I wanted to do physics. Because of a good high school teacher in physics who managed to make it like very exciting. You could see how it explained all sorts of things very easily. And then I read a couple of popular books, one on relativity and one on quantum mechanics, which are like the basis of 20th, 21st century physics. And it like blew my mind because it was full of strange things happening, like time dilation or the uncertainty principle, where it was just amazing. And I thought, well, there's no way I'm going to understand that better myself. I'm going to have to go and get taught it. So I decided to go to physics. And that went okay. I went to a highly respectable but not stellar university. And then I applied I thought, this is great. Now I can do research. I wonder what research is. What I thought was, well, I want to find things out. I want to find new things and try and understand them. And there seemed to be an awful lot left to understand. So I thought I'd do either astronomy or like accelerator physics. And then one professor at the university I was at showed me a published paper in astronomy, and it had like 3 names on it. And he showed me one in accelerator physics, and it had like 200 names. And I thought, well, there's no chance of standing out among 200 people. I'll go the easier looking route. So I did astronomy. But it had to be something like one of those because it was like big. It seemed to have enormous implications for the basic physics. And so I applied again. I applied to PhD places, and none of them that wanted me were very interesting somehow. This is one of these strange things that you apply not really having enough knowledge. So there was this field of cosmic ray physics, and somehow I just knew that was boring. And I think that was completely correct. And I have no idea how I knew that. So instead, I went and did a master's degree in astronomy, and that turned out to be a great move. It was just a 1-year program. So I learned some actual astronomy there, and then applied for PhDs again. And by a stroke of luck, I was rejected by Cambridge and accepted by Leicester University, which at that point no one knew about. But it turned out the radio astronomy group at Cambridge that I was applying to were peaking that very year, because the US opened a much, much bigger telescope called the Very Large Array that year and kicked their thing into the dust, right? So it was a good moment not to go there. Instead, going to Leicester was great because they just launched, when I arrived, the second ever satellite to survey the sky in X-rays, and X-ray astronomy was a completely new field. It just started like 10 years earlier, and there were a few dozen sources known in the sky that were emitting X-rays, and no one knew what they were, more or less. And so we surveyed the sky and kept finding all sorts of new and exciting things that no one had guessed would be X-ray sources, and including what my PhD was on was finding out that what we now know are giant black holes are great sources of X-rays, which are the darkest things in the universe, are actually emitting enormously intensely. But it's not the black hole itself, it's the gas falling into the black hole. It gets really, really hot because it's got the strong gravity of the black hole makes it makes the material move very fast, collides, gets enormously hot. And so that was a surprise, and that was very lucky for me. But it's a general thing. If you're going to once you get to this point of choosing to do research, if you want to do that, I would recommend getting into some totally new field, something that's just beginning. That's been demonstrated enough to know that it's got a long way to go, but hasn't got so far that you have to get into very sophisticated kind of analysis or anything before you can publish so you can be the world expert, because nobody's the world expert because it's totally new.
Yeah.
So that's how I think I was lucky in finding that route.
Couple of cool things that I think are worth, reflecting on in the story. And thank you for sharing that. The first is that, there was a teacher that made a subject matter in high school for you a very interesting subject matter. And that in its own right, that genuine curiosity and desire about that subject leads to additional exploration for you. And hey, this is, I think, where I want to go. And then continuing on to the college route, some of it, or sorry, I should say the postgraduate degree, but some of it was luck, right? Some of it was you didn't get into this one, and this one took you. And so we share a lot with families about trying not to fall in love with a particular institution, because you just don't know the outcome until they decide that you're either worthy or not, right? And whether you were worthy or not is not the question. In retrospect, obviously you were worthy of all of it, but you sort of lucked out from the sounds of the story of getting into the other school that had a different opportunity. And then I think the other thing the advice is so amazingly clear. If you're going to get into a subject matter and you want to be involved in research, don't be involved in something that's been around for hundreds of years and has been researched thoroughly, and then the nuanced space you have to get into, you've got to catch up of 300 years of research. You get into something in research and it's brand new. Hey, you are the expert by virtue of being in the field, right? So let me ask you another question: research versus teaching versus application, right? What made you want the research side? Was it the curiosity versus doing something to teach others, versus using it in an applied space? And was there even an applied space that you could have gone into?
Let me think. So for me, it was absolutely curiosity and just wanting to know things that were new and find them out. And somehow that I don't know how I got that passion, but that was real. Okay. And a lot of people went into teaching directly from, into teaching to get diplomas right out of high school. And I just didn't like that because it seemed like all I would do is recycle the knowledge I'd already gained. And that wasn't good enough. I wanted to expand that knowledge. So for me, it was not a good choice to go into teaching. I think I would have been very frustrated if that had been all I did.
Okay.
And applications, well, my whole family are engineers. So the question when I was going to high school was, well, what kind of engineer do you want to be, Martin? Mm-hmm. Right? It was like, what else is there? Right? And somehow I really didn't like that either. Because again, engineering was applying knowledge that already existed. And that's fine. And it's really good. Then you don't get anything done without engineers. You can't really build anything. But it wasn't for me. So,
okay.
Yeah, that's
so
about it.
And at that point, again, Joe, one of the subject matters that comes up to us all the time is it's as important in this journey of higher education to know what you don't want. And right. I think there's a critical component there where you were like, I don't want to just recycle knowledge that I have currently. I want to expand my knowledge. Secondarily, the application of the engineering, as an example, is they're making new. Yeah, they're sort of expanding engineering, right? It's not like it's a finite thing, but it is, you're applying the same rules and the same things over and over again, and you're limiting the creativity and the exploratory nature of what you do today in the astrophysics and the black hole research and the subject that I really want to get into, which is the asteroid mining. But this concept of having a little bit of self-knowledge as you're going through your journey in higher education is a vitally important component of having what I call luck, right? Luck favors the prepared mind. So if you are not preparing, and in some cases it's cutting things out, I'm not going to do that. I don't want to do that. I know I don't want to do that. Because a lot of people in your situation with a family of engineers being asked, what type of engineer are you going to become your whole life? They just do it. They just, well, I guess I'm going to be a mechanical or I'm going to be a electrical. And they kind of just go through it and realize, at age 35 or 40, I hate this. I don't want to do it. And, lawyers are another one that, and I'm not going to get off topic too much here, but the amount of people that have said to me, and I never knew this was an expression, but they call themselves recovering attorneys. And I said, what's a recover? Someone that did it because, hey, it was high paying, it was glamour job, it was you could either be an engineer or a lawyer, and I was bad at math, and so this is what my parents said I had to do, and they reversed course, and so that's a thing that is a tough lesson to learn when you're in, you've started a family, you've got a mortgage, you've got all this stuff, all this responsibility, and you chose poorly. So kudos to you for the self-knowledge and kind of pursuing the passion, which is the other side of that. Any advice that you have on the people sort of exploring this field? Is there, like, if I'm a prospective student and you're obviously now in your career, you are the expert, there's no question. And so is this a field that has so much more to go that you can, it's almost infinite? As they say the universe is, right? The research can go, or is this a field that people should lean into if you have that passion? What's your kind of opinion on that?
Oh yeah, I think there's a whole. The James Webb Space Telescope is demonstrating that there's an enormous amount to go. For among other great new things that are happening. We're looking at the earliest galaxies to form in the universe, back to the time when the very first stars formed. And at some point we should finally look very different, but we haven't quite found that point yet. At the same time, we can look at planets out in solar systems other than our own, and now start to not just find that they're there, which has been happening for like 20 years now, but start to understand their atmospheres. And maybe eventually with the next generation of bigger telescope, we could see whether there are traces of life in the atmosphere. And so there are even ideas, and which may not be ever practical, but may be eventually practical, to send a telescope out well beyond Pluto and look back toward the sun, and the sun will act as a gravitational lens and will image planets around other stars. So you could see continents and oceans and even finer detail on that. So you could start to really understand that. That would be pretty darn amazing.
Yeah, no doubt.
And there's other fields too. Gravitational waves, completely new. Neutrino astronomy has got like a few neutrinos have been found, but they're going to build a 10 times bigger detector, and that'll make all the difference. That'll be like X-ray astronomy was when I started, I think. So, yeah, there's lots of areas that are still way to go. Yeah,
and again, I just want to relate it back to most of our listening audience here, which is, I used to talk about. And probably when you were growing up and they were talking about engineering, right? Engineering at the time, there were very refined subject matters of engineering, right? You had your electrical, mechanical, your nuclear was a relatively new subject matter. Chemical was a relatively new chemical engineering. We had chemistry. We've always had chemistry, but that chemical engineering component and all that. And so like you had these, I don't know, the big 5 or the big 6, but now, I mean, there's 30 different engineers. It has just expanded and expanded and expanded. What you're sort of saying, or how I'm interpreting it, and I want to make sure I'm not taking your words, is we're discovering new studies and almost new levels of degree that need to be attained in some of these areas of research, right? It's no longer just astrophysics. That's your base, and then there is a subset in there that is specific to the things that you're talking about. So we're expanding the almost professional designations you can get. Correct?
Yeah, astronomy several hundred years ago used to be like a piece of mathematics. They would get a degree in mathematics and do astronomy, because all you were doing is plotting the positions of planets and our planets in the solar system on the sky and things like that. And then when the invention of spectroscopy in the 1850s, it was possible to know what stars were made of. And so it became astrophysics, because suddenly astronomy was able to do physics of the things that we're looking at. And now we can see it moving, a large fraction of the field is moving into astrobiology, right? And that needs astrobiology, actually, life on other planets. It's not just biology. You need geology, you need atmospheric physics to understand the cycle of the different elements and chemicals in the atmosphere. So it's getting to be very rich as a field. Yeah,
I love that you said astrobiology, because it's that idea that, okay, the subset of knowledge base you needed to be an astrophysicist is one thing, and now all of a sudden you're studying and you've got to bring biology background to it, and you got to bring geology background to it. So that now creates a coursework or a body of study that requires a different subset to get to that level of thought. And so while it is completely new and separate in its own right, it is pulling some of the other pieces into it, and it's the expansive nature of different majors, right? I mean, it's how it works.
Right. Yeah.
So I guess, one of the things we talk a lot about, and we've heard different things about, is, planning with the end in mind, and then creating a roadmap essentially backwards to where you're currently at. And so, your roadmap wasn't essentially, I don't think, like you said, there was a lot of luck, and we talk about luck being prepared, but it seemed like it was just every step of the way. Oh, this is what I want. I know I don't want that. Oh, this is what I want. Was there anybody that helped you kind of create that? And for students that may be interested in this and are thinking about potentially being a researcher, where should they be starting? Where should they be looking at as far as their type of roadmap? What's kind of some of the steps that they would take, or what are some of the steps that you took that they can also learn from?
Oh gosh, I think I had very little information, and I don't think I got a little bit of guidance from my physics teachers, but not much. Mm-hmm. There was a book of pretty simple back then. There were like 50 universities in the UK, and you could look up what they each did. They had a little syllabus of, we do physics and this is what we cover. And you could look up that. I actually chose one because I wanted to do a minor in philosophy. And it turned out I was very ill-suited to that. So I didn't actually do more than a couple of classes. So, but that cut it down to like 3 different places to apply. And I apply the form back in the day in the UK, you apply to 6 places, and that's the total you're allowed to apply to. And then they work it all out between them. And so I got into my number 2 choice because Oxford said, you're not doing theology, so no, you can't come in, right, to this college. So I got into that next one. So, and did I have advice? I had a little bit of advice from a mentor who was an old geezer about my age now at Bristol University, which is where I went. And he helped me make a small telescope mirror. And he was an optics guy rather than an astronomer. But he helped me talk to a retired professor in Oxford, which may have helped me a bit understand what to do. Then let's see, on my master's, it was 1 year, and I think I didn't have a clue really where to apply to. I found a list of universities and various Canadian universities that really had nothing to do with astronomy that I found. And so it was all pretty useless. I did, but there were talks. At the master's level, you go to the seminar every week where some astronomer comes in and talks about what they're doing. And mostly, I vaguely knew what they were talking about, but not much. But then one of them was Ken Pounds, who was at Leicester University, and he talked about X-ray astronomy. And he's a very good speaker. And he made it very exciting and clear that this was totally new and full of puzzles, that we didn't understand this or that. And so that's why I applied to Leicester University. And I applied immediately to Leicester after my BSc, and got turned down because a guy with a slightly better degree had applied, and they had rules where you had to, because of levels of grades you get called first, second, upper second, lower second, and so on in the UK system. But basically a grade on how good your degree was. This guy got a first, I got an upper second. So he got the A and I got the B. And the rule was they had to take him. And that was another stroke of luck, because he spent years building a rocket payload, which would have been wonderful if it had worked, but it span out of control. And so he got nothing, essentially, for his PhD data. You have to really scrimp around and find odd bits, on the floor that he could use. So it was, and I would have been very ill-suited to building a piece of hardware with electronics, because when I demonstrated in lab classes for the undergraduates when I got to Leicester, I would make smoke come out of the back of the equipment. And it was really not what you're looking for.
Not your thing.
No. You had to be much more disciplined and careful than I had ever been, and probably still are. But we just got, everything was starting to work on computers, and they could make mistakes, and you just change the code and run it again. That was okay. I could do that.
Okay.
And I think, a big takeaway I have from that story is, as much as, you keep saying, oh, I got luck, this was luck. And again, there's some fortuitous events in your life, but I'm also hearing, well, I looked into this many schools, and I knew that these were not a fit. And I researched this type of program and realized that was not for me. So it wasn't as much, I got into a school and it all worked out. No, you put work in to figure out what was a fit and what was not. And that, I think, is an extremely important. Like, there is work, especially in the world today, and how much knowledge you can get that was different back then, as far as just the amount of knowledge we can get with the internet and different college planning network. Like, you can really start to rule schools out, and that is extremely important. And it may not be that you should be always looking at the name of a school. It's what are they offering? What programs do they have? How many people are in that, program? And we talk about competitiveness. Sometimes if you're going to a school and you want to study a certain subject matter and they're known for that, well, is that where you have a place to shine? Or do you go somewhere that's now just trying to start their program and you can be the top student and potentially just grow and help build that program? Like, there's a lot of work that can go into finding the right fit. And it's not always about luck. But as Dave said, I always love that luck favors the prepared, right? So, yeah.
Yeah, that's great. Right. That's very nicely put. Thank you.
Yeah, I agree. Nice summary.
I try sometimes, you know.
So now, what I've been waiting for, and
here we go.
Okay.
Two questions. Well, I guess I'll start with the first one. So everybody's watching Elon Musk's, the Richard Bransons, the guys are now investing personal wealth of an extraordinary nature into space travel, into space exploration, into knowledge. How much has that impacted your profession, and having now not, like, for a long time, space was government managed, really everything. Every dollar that went up into space was via governments across the globe. Now we're starting to see these massive stockpiles of wealth invest in that game. Has that propelled your industry? Has that propelled your research? Is it helping or is it hurting?
So far, it's had a minor impact, I would say, but that doesn't mean it's going to stay that way. I mean, now several small satellites have been launched on the Falcon 9 rocket of SpaceX, Elon Musk's company. And that's good because it's saving money and making them more capable. I think the test satellite was one example of that. It went into a very special orbit, and you could do that because it had a Falcon 9, which is more powerful than the original plan, I think, if I remember correctly. And that's a satellite that's been finding many, many more exoplanets, planets outside around other stars than the sun. And very valuable. And so there's a few cases like that. But I think it's going to be a bigger impact as time goes on in a couple of ways. One is this Starship, huge rocket that Elon Musk is getting, is trying out. He's all set to go again, so long as he gets permission to launch. And eventually, I'm betting, given the track record, that will work fine, and it will mean you can launch enormous masses to orbit. Weight of spacecraft can be 100 tons instead of 7 tons. James Webb Space Telescope weighs only like 7 tons.
Okay.
And to get that light, they had to make ever so special thin mirrors, which made it was very hard to maneuver them. And to get it big enough, they had to fold everything up. So the big unfolded mirrors was much bigger than the rocket that it went up in.
Okay.
And a lot of that, and Musk's new rocket will be, instead of, it's all done in metric, 5-meter diameter is going to be 8-meter diameter. And so you could plop the James Webb Space Telescope mirror in without any folding, and it could be thick because the mass is, there's plenty of mass budget to deal with it. And so it could usher in an era when we suddenly can make really powerful telescopes much cheaper than we're used to, right?
Okay.
I'm hoping I've written a paper about this, and I hope it has some impact, and I think people are going to start looking at that. But that's actually the short-term difference. The long-term difference is going to be that by 2030, there will be at least 2 very plausible commercial space stations, that is, free-flying, independent of NASA, leased by NASA, parts of them for research work, but also leased lab space for any country that can afford about $100 million a year. They could get an astronaut in orbit most of the time, or even a rich corporation. And some biotech companies might well find that it's worth their while sending up research scientists to do their research in zero-G. So I think there's going to be beginnings of research economy. We already have tourism in space, thanks to the billionaires. We're going to have tourism, we're going to have research, and eventually the research will lead to new products. Amazing things like maybe you can grow a human heart in orbit. basically by 3D printing it. And in cells are squishy things. So if you 3D print on Earth, they kind of go like that. But if you 3D print in orbit in microgravity, they keep their shape. And so it's a possibility. There is a company looking at this. Who knows? Eventually it might work. So you could order a new part from a space station for yourself. And that would be nice.
Yeah. And Bezos will take care of the shipping.
Well, yeah. Right.
No, I mean, it's fascinating. And, that leads to the kind of further conversation, which is where you are the world expert from all my research in the idea of the asteroid mining and the potentials there. So, I look at this and again, you have to excuse my ignorance, but I look at the movie Armageddon, right? And Armageddon, they're flying up, they're landing on this asteroid, they're blowing it apart so it doesn't hit Earth. But the idea behind it is essentially, can you land on it and mine it for the precious metals or the valuables that are there? And can we bring that back to Earth for, and in the introduction to this, it was, what is on an asteroid? Like, what are we going to mine on the asteroid? So that's question number one. And how is this conceived? And is there a timetable where this is a reality? Like, will I be alive? Will you be alive? Is this something that is really just not that? If the asteroid's close enough, the technology's close, this could be something that happens. Can you elaborate a little bit on the subject matter of asteroid mining? And then your research obviously has been extensive on it. Thanks everyone for being a part of College Knowledge, powered by Elite Collegiate Planning. Just as an FYI, we are guaranteeing that you will save money on college by working with ECP. This is a guarantee that you will pay less. Book a free consultation at elitecollegiateplanning.com.
Yeah, sure. So the point of these space stations and the growing industry in orbit is that they will soon need more supplies than it's sensible to get from Earth. They might want iron for construction. There's some people thinking it's now sensible to rethink the idea of space-based solar power. So you could have big solar panels, square miles even of them in orbit, and permanent sunshine, and then beam down using microwaves the power to Earth where it can be received. I don't know if that's practical, but I know that people are relooking at it. It used to be completely absurd. For that, you need enormous amounts of construction material like iron in orbit. And although SpaceX will be able to launch 100 or 150 tons at a time, that's still not that much. And maybe there are some pure iron asteroids out there, we think. And there's a mission called Psyche that's going to investigate the best candidate, launching fairly soon. And maybe we could mine those, cut out a piece of iron, bring it back to where we want to use it. And energetically, it's easier that way than bringing it from Earth. Whether economically it is, we don't know yet, and that sort of changes depending on the technology and the economics as things go along. So it could be for use in space. And it's not just iron, there's also water on asteroids. There's a lot of water in the universe. Hydrogen and oxygen are very common elements, and that's the simplest thing they make. And so there are asteroids that are a good fraction of water, 10% water or something like that. You could boil the water off at the asteroid and just cart the water back to orbit. So, maybe the millionaire tourists would prefer a toilet that really works in orbit rather than the ones they have now. And a bigger water supply would really help with that, and having a shower and stuff. And they're going to have needs that this may be able to fulfill. The only thing that could bring back to Earth, actually land on Earth and sell, that is worth bothering with, what are called the platinum group metals, right? Okay. Platinum, palladium, rhodium, and so on. Platinum and palladium are the most expensive things. They're worth millions per ton, tens of millions per ton. And because they're very rare on Earth, and they're very rare because when the Earth was molten, they sank down into the core along with the iron. They melted, they dissolve in iron. So there's plenty of platinum in the Earth, but it's thousands of miles beneath our feet. So it's easier to, you can never get that. But the same thing happened to the predecessors of the asteroids. They melted like that, and they had a core of iron full of platinum and palladium and what have you. And then they got broken up by collisions. And so you get a pure blob of the interior of this early body. And some of those are rich in platinum. So maybe we get that out and sell it. But it's tough.
So, and I didn't mean to interrupt, but is this, so again, how many asteroids are flying within a range where we could get to them? And what is the actual reality of landing on it or putting a structure on it and being able to do this?
Okay. One of my first papers in this field was to say, actually, there really aren't very many that we can get to that we know of right now that are worth some nominal number like $1 billion. Because, what venture capitalist would wake up with that if it was less than $1 billion? I worked out how many are the right kind of asteroid. Of those, how many are rich in platinum, say, or water. And how many of those can we actually get to, given the rockets we have today? And when you multiply all those things together, I ended up with 10.
Okay.
So that wasn't a very encouraging answer for asteroid miners. But it meant of the ones we knew that day, and now there are 2 or 3 times as many, and we're going to find another few times as many soon because of new surveys that are going to start in the next couple of years. And then, so it gets up to 50 or something like that. But the new rockets, in particular Starship, are much more capable. So instead of only being able to access about 3% of the asteroid population nearby, we could access half of them, and that would multiply it up by another 10 times at least. So it could be several hundred accessible by 2030 or thereabouts.
And is this the type of thing where let's say all things are real moving forward and we're able to do all this? Is this something where you get to the asteroid and you change its trajectory towards a specific direction and you're trying to get it to orbit so that you're, or is that an impossible feat in its own right? Are we just getting to it, mining it, and leaving it?
Going there, mine it, and leave it is by far the better thing to do. But it means much more advanced robotics, right? Than people moving the whole thing and then having people mine it in an Earth orbit. Okay. I think you're going to get a lot of pushback if you say, I'm just going to get this 100 football stadium-sized rock. I'm going to push it towards Earth. Don't worry, nothing will go wrong.
Nothing bad could happen.
Nothing could ever go wrong with that kind of... that's going to be undesirable, I think. So it's going to be a while before anyone lets you do that. You have to demonstrate a lot of capability. But so extracting water is quite easy. I said you just boil it off. Extracting the platinum is going to be much harder because it's like 1 ounce of platinum per ton of rock. Okay. It's tricky. Also, by the way, you don't really land on an asteroid. The recent OSIRIS-REx mission that just had its sample returned to Earth into Utah, in the desert in Utah. It tried to land on the asteroid and then it grabbed some rocks. But it had this arm, which is like a yard long. And instead of stopping on the surface when it reached the surface, it just went straight on in. The surface of the asteroid flowed around it like a liquid. And it's a strange property of what are called granular materials in zero-G, that they become like liquid like that. So they were lucky to escape. It also planned, but
So they knew that was going to happen.
They were not really up on it, no, but they pre-programmed that it would fire little rockets to push back after a certain time.
Okay,
at least that's what I understand. Yeah, I think they were quite surprised. So it's dealing with an object that has almost no gravity, a long way from home. We're going to have to do a lot of learning before we can do that well, I think.
And had those rockets not deployed, would it have just absorbed it? Would it have just kind of sunk into the...
Quite how far it would have gone, I don't know, because that was a long thing like that, and then there's a big spacecraft above it. So that might have been enough to stop, but we don't know.
Okay. So where? Go ahead. I'm sorry. Go ahead.
Other ideas are you wrap the entire asteroid in like a plastic bag or something like Kevlar thing, and then cinch it up, and then you can process it a bit at a time like that. But you hold it together with tension instead of gravity. So
as a very ignorant person on the subject, me, if we get to an asteroid, let's say, and we're able to bag it up or do any of these, how long of a period of time do we have on an asteroid before there is either, it's too far away where we can't get back to it? What direction does it have? Is there a specific direction or vector this thing has to be traveling to actually make this viable for us to get off of it and back to either a space station, as you say, or even to Earth if it's the rare metals?
Yeah, that's why there was such a small fraction we could get to. Is that with the rockets we have now, we can really only get to a few percent, because they have to be in orbits that are almost the same as the Earth's, but just make it be a little inclined, a little further out, a little further in, but pretty much in an Earth-like orbit. With a powerful rocket, you can change the orbit, your spacecraft orbit, a lot more, and so you can get to them. Typical journey times for these are about 6 months there and back, there and 6 months back. But you have to stay there until the asteroid comes back into the right location, and that may be a couple of years.
Got it. So in the, again, trying to understand, and again, you've spent your life and career studying this, so I don't expect to understand it in short order in a 45-minute interview. But if the asteroid is, first of all, is there a distance from the Earth where we lose our orbit? Obviously, like, you get outside of it and you can't be in orbit anymore because the mass of whatever the spacecraft is, or the thing orbiting, is no longer, the gravitational pull is no longer strong enough. Does it just fly into space as the movies would show you, or does it find another object, and does it stay in the sun's orbit? Does it go to another planet's orbit? And how would we, I guess it's pure mathematics at that point. I mean, I don't know what math does that. I'm sure it's very high level physics, calculus, and all that. But it seems to me that, we get our satellites in orbit, so they stay circling the Earth. But there's other larger objects out there that have gravitational pull at the same time. How far away from Earth can you get before you're sucked to a larger object? If that even makes sense. That's just my simple brain.
I don't know if you've seen these diagrams which show these sort of wells, the gravitational wells. The sun is huge like this, and then the Earth's a little dip, and the moon is a tiny dip, and then Jupiter's out here with a bigger dip. So what you're talking about is getting out to where it's kind of flat. You get out of the Earth's potential well, and you go into the flat area, and then that means the pull from the Earth is balancing the pull from the sun and other bodies. And so the first thing that happens, you get escape velocity from the Earth, and you will never come back to the Earth. But now you're in a solar orbit, and you have to get it much faster than that to escape the solar system altogether. And the chance of accidentally going to, say, Jupiter is tiny. But if you aim for it, you can aim for it and get in orbit around Jupiter, as of course NASA probes have done.
Okay. Fascinating. I go all day. So give me ideas of, you've watched technological progression over your career. We're obviously significantly more advanced today than we ever have been. We've got artificial intelligence. We've got robotics that are making advancements. How far are we from being able to do any of the types of things you're talking about in the asteroid mining?
I think the technology of doing it is relatively advanced in most areas. What we're waiting for is the in-space economy that I was talking about, manufacturing optical fibers, for instance, that it can be super good if made in zero G. For that to develop so that it creates a demand in space for some of the materials you can get from from asteroids. So we'll see how fast that goes. I'm kind of optimistic, bullish on that thing, because I suspect once you start having serious scientists working in orbit and on already promising projects, one or two or three of them are going to turn to products within a decade of doing that. So by late 30s or something, I think there could well be a beginning of enough demand in space that you would start saying, those asteroids, they're looking pretty tempting. We'll have learned a lot by going to the moon and doing exploration on the moon in the meantime, because that's happening now in this next decade. And that'll teach us a lot.
So that's an interesting concept here. I want to chat for a minute. So the moon itself, it was, and I'm not going to get controversial here, but we've landed on it. So we say, right?
Yes, we have. Yeah.
Okay.
And Buzz Aldrin will fight you if you say anything else.
I'm not, but why haven't we gone back to it until now? Why has it been something that we haven't explored more? Why? So we've spent a lot of time with satellites. We've spent a lot of time in orbit. We've had people in orbit for a year. I've seen all that. Why not the moon sooner than now?
I think because it looks like a great ball of dust and craters, and it's not very interesting to most people that way. But it turns out that first impression that you got from the Apollo astronauts bouncing around on the surface is misleading, right? Okay. And it took a long time for anyone to go back to the moon, like 25 years. And then finally, there were one or two experiments that started photographing the moon in different colors and could pick out geological features. And there are other techniques where people discovered that there's probably a lot of water in dark craters, permanently dark craters at the poles, the north and south poles of the moon, which never see sunlight for the past billion or more years. And so all that means that, there's actually some interesting places to go here. And particularly water is great for, if we wanted a human base, it provides life support, not only for air, oxygen in the water, but also water for hygiene, of course, and drinking. And but also growing food, because you can actually have a fresh salad instead of trying to bring one from Earth, which is hopelessly expensive, and it would be kind of limp by the time you got it. So it changes the whole look of the moon for humans to go there.
Got it. So it's more the check the box, move on. Let's get capabilities up elsewhere. And now all of a sudden we have more information than we did previously, and it makes it a more interesting kind of subject matter at this point.
Yeah, much more interesting. People talk about mining helium-3 from there, and there's some places which are particularly good for mining helium-3. And I laughed at that because it's to put as fuel into fusion reactors, and we don't have fusion reactors. And to use that particular kind of element in a reactor is even further off. But it turns out helium-3 is actually very useful in cryogenics, making things very, very cold. Turns out to be kind of vital to get, and that's important now for quantum computing. And so, whoa, that's big money. And if that works, so if that works, then there could be a huge demand to actually mine this helium-3 from the moon.
And I'm assuming that the advancement in rockets and the private sector is helping that type of exploration again, because we can send bigger, we can go further, we have that power that maybe was a stretch to do regularly historically.
Right. So the astronauts on Apollo could bring back 10 pounds, 20 pounds, even 50 pounds of rocks. But the lander that NASA is planning to use for the Artemis program to return to the moon with humans is a variant of the SpaceX Starship. And that's going to be able to carry more like multiple tons tens of tons back to Earth, or off the moon to where it will be transferred to something. It's a complicated arrangement. Yeah, you're talking multiple tons instead of multiple pounds.
And are we sophisticated enough to land where we want to land on the moon at this point?
Well, we're getting better. There's because the moon has been photographed so in detail at such fine levels now. You can store all of those images in your onboard computer, and it can match the terrain in memory with the terrain it sees right below it, and say, "Oh, I'm here. I can get down." And it's certainly better than half a mile or something like that. But you really need to get better than that, and it's being worked on. I'm pretty confident that's going to work. The problem is at the South Pole, the places you want to land are about the width of a football field. It's long.
Got it. And they're very dark, right?
That's got to be pretty good.
Okay. Is there a case for any, and do we know what the makeup of the moon is? Is there any of the mining type stuff you're talking about, asteroids? Is any of that, are we bound to do that stuff on the moon?
Certainly we can. Extraction of water is the first thing, right? That's the most enabling resource there is. After that, there are places that are iron rich, which are probably debris fields related to asteroid impacts in the past. And we need to map those out more carefully to find the richest places to go. But there's very likely quite rich iron deposits. Some radioactive elements, thorium, is possibly available, is available, and maybe we can find rich deposits. Again, we've got to, when I say we know the moon has a lot of stuff like this, it's been mapped at the sort of 1 mile level, and you need to actually go there and get something useful. You've got to get down to the, 100 yards or less, 10 yards, so you can say, this is the place to go. So that's work to be done. Surveying work still got to be done.
Now, again, in my ignorance here, I've been taught, and I know this to be true, that the moon has a lot to do with the tides on Earth and the gravitational pull and all that. If we go up there and disrupt anything, does that disrupt that type of feature on Earth? Nothing. We're not going to mess anything up there. No,
we would have to remove a big fraction of the moon's mass. To affect the tides, and it would reduce the tides. And the moon is only half the tide anyway, and the other half is from the sun. But realistically, no, I don't think we're not going to mine the moon so much there's a big change in its mass, so it won't affect that.
If it turns out that
whatever we do to it, taking any amount of mass away, doesn't change the orbit of the moon at all.
Got it.
If it turns out that there are valuable resources that can be mined on the moon, it's obviously not owned by a country. It's, so is there I don't want to say a war, but is there a battle on who now hires SpaceX? Does China, does Russia, do they essentially now say, hey, we're going to pay you this, and now we get to go where we want? And what's going to be the, I'll say, where's law going to come into, is it that we put a flag on there so we own it? Like the United States owns it because that's our flag. How are we going to get around that aspect of things?
This is something that I've been talking about a lot, that needs raising, because a lot of the enthusiasts for going back to the moon or for mining asteroids are not sympathetic to lawyers or governments in fact, in many cases. They just like the pioneer going out and doing it themselves. Right?
Sure.
Like, it wasn't really like that in the West, if you go into the history of it. And for sure, there's going to be a problem. Planting a flag does nothing. There is one piece of international treaty that everybody has signed up to, and is called the 1967 Outer Space Treaty, for short. And it clearly states that no celestial body, including the moon, is subject to national appropriation by any means. Right? So you can own the land. Now, the difference is you can, if you pick up a rock, like the Apollo astronauts did, then it becomes property, and that's yours, right? And there's precedent from the Apollo, from the lunar cod, from the Japanese missions to the asteroids, and now from OSIRIS-REx. But that's kind of settled law, and it was a little controversial when it was raised again by the asteroid mining companies, but a whole bunch of countries have signed that explicitly into law. But there's nothing to say who gets to pick up that rock from that place.
Mm-hmm.
Right? So if there's one place on the moon which is super rich in a valuable thing, right? And we suppose company A did a lot of work and went from this 1 mile map down to a 1 yard map and said, I found it. This is it.
Yeah.
Then another company B could say, oh, company A has found the good place to go. And we didn't need to do that researching because we see where they are. So we spent our money and set on a much bigger mining machine. So we'll land that right next to them and start crunching away, and we'll get all the profit. So nothing regulates that right now.
Mm.
So that's sort of claim jumping going on. There's nothing to stop that.
If I heard it correctly, it's finders keepers.
Pretty much. And
if you can take it, it's yours essentially, right?
Yeah, yeah.
Possession is more than 9/10 of the law in this case.
That's right. Yeah, once you've picked it up.
One other thing that I want to just touch on, because I think it is a subject that you've mentioned over and over again in your kind of answers to us, which is economics and the financial component of this, and the reality of and. I mean, it's obviously always been there. But historically, it was always governments that were involved, and so taxpayer dollars funding a lot, right? In this instance, you have an economy that you've got to figure out. You've already talked about the expense of getting and actually doing these things, and is there a market for it? Essentially, right? If you can't, you're not going to go mine something you can't sell, bring back, or use, right? And that someone's unwilling to buy. But then you also have this, the economies, and this is where I was leading with the private sector money, right? Where you're not going to be able to mine the first thing you find that is worth dollars, right? There's a lot that gets to going there. How much is the economics of this? Has it been exercised, and where do those cross disciplines come in? Where someone's got to, I mean, you're an astrophysicist. Obviously you understand this. Have you studied the economics of it and the actual finances? And is anybody doing that work?
Yeah, there are a few people doing that who are still a couple of asteroid mining companies started up 10 years ago, and they both went out of business, out of the asteroid mining business anyway. They got bought for their technology.
Okay.
But there's still some companies starting again to do this because 10 years later, everything's different. A lot of things are different. We know a lot more asteroids. The rocket technology is much better, and so on. They are doing it, but they keep that to themselves because that's their business plan, and that they have their secret source. They won't tell me. Very wisely, they won't tell me what their economic analysis is. There isn't a lot going on. There's, across the river here at the Harvard Business School, there are a couple of people who are working on space as a business proposition. Professor Matt Weinzel is the person I know best in there. So I think that it's starting to come into MBA programs a little bit. With him as maybe one of the leaders. There are people at the Colorado School of Mines who look at the economics more than I do. So it's beginning, but it's pretty minor, I think, activity at the moment. It'll kick into high gear if Starship really shows its potential to bring costs down dramatically. Another 10 times cheaper rockets. That will change the economics utterly.
Yeah,
and
absolutely.
Not always in the favor of asteroid mining, because it means bringing stuff from Earth will be cheaper. So it means you can do asteroid mining more easily, but you can also just heft stuff from the ground up more cheaply. So it's not a simple equation.
No, absolutely not. And it's that's the fascinating part to me, having an economics background and going, hey, what's the reality of doing this? You know, can we make it happen?
Yeah, there's going to be a whole lot of different professions needed if the space economy gets off the ground.
Without question. Well, this has been tremendous. I love it. Hold on. Niall's got a question burning in his brain here. Let's see what he's going to bring to the table.
So, Dr. Elvis, I know you've studied a lot about black holes. Has there been research of what happens when, you know, an object enters a black hole, or have you guys spent any sort of spacecraft or observational tools into a black hole, and where does it take you? And
the nearest black hole we know about is a very, very long way away, thousands of light years, 1,000 light years. So that we're pretty safe on that. The theory is that once you drop something into the black hole past the event horizon, nothing escapes. The light doesn't escape. It can't send any signal back to us. And the Event Horizon Telescope images of this black circle with the bright orange rings around it kind of confirms that pretty solidly. That's the shadow of the black hole that we're looking at, and nothing is getting out from inside. And so it's very hard to know what's actually on the inside. And it's a basic physics puzzle, fundamental physics puzzle that Stephen Hawking and many others have been trying to solve, but I don't think they really have a solution yet.
Okay. And yeah, so when we had our interview with the gentleman from Penn State, he had mentioned we might possibly be living in a black hole. Can I just get your take on that real quick? Just my curiosity is I need to ask that.
I think he might be referring to the whole universe, which is part of Stephen Hawking's thesis, that the whole universe could be like a black hole. Mm-hmm. But otherwise, no, we're not living inside one, because we can see. Our view of the universe would be terribly distorted and it isn't if we were inside. So no, we're safe on that.
Thank you.
There is an idea that there's a ninth planet, not meaning Pluto, but yet another one, a few times the mass of the Earth, orbiting and kicking mini planets in what's called the Kuiper Belt into strange orbits. And one proposal is that is, in fact, a baseball-sized black hole. So it's pretty unlikely, but it would be great fun if it were. And it's still a safe distance away.
Amazing. I had so many questions, Niall. Thanks for that. But we're about out of time. I can't thank you enough for spending this time with us and educating us, and kind of I really appreciate the beginning parts where you shared your story and kind of the mentorships and the options and the way it kind of worked out for you. I'm fascinated by the subject. I think this has been an incredible interview.
Oh, great. Happy to help.
This has been great. Very enlightening for me. I think, I've always, as Dave may have alluded to, I'm always a little, it's not my passion, the stars and the study of them wherein, but hearing, the one thing that stuck out about potentially, 3D printing a heart, and the fact that if you do it in space, it's different than if it's 3D, like that is pretty mind blowing, and, things that I would never even imagine. So it's, I didn't either.
It's amazing. Yeah,
it is.
But this really was very enjoyable, and thank you for your time.
Great.
All right, everybody.
Absolutely a pleasure.
All right, everybody. That's Dr. Martin Elvis, astrophysicist from the Harvard Smithsonian Center for Astrophysics. Thank you for being on the show.
Pleasure. Bye.
Thank you guys for being a part of College Knowledge, powered by Elite Collegiate Planning. If you didn't know, we have a free crash course on college funding at elitecollegiateplanning.com. This will explain different types of loans, types of financial aid, savings vehicles, and much more. And remember, plan early and pay less. Thanks for listening to the College Knowledge Podcast with your hosts, Dave Kozak and Joe Kerins. We hope you enjoyed this week's exploration of higher education, sponsored by the College Planning Network and Paradigm Financial Group. That's all for this episode. See you next time.